Good day and welcome back for the third part of our discussion on sequences. In our previous videos, we've introduced the concept or idea of a sequence, simply a list of numbers with a definitive order. And the key question of interest for us is going to be, for a given sequence, can we determine the limit as n goes to infinity? That is, does it converge or diverge? And if it converges, what is the value of the limit? In our previous video, we introduced, or maybe I should say reminded ourselves, of key limit laws that we've used throughout our entire calculus journey, as well as a couple other properties specifically related to sequences. Which means we are now ready for a few examples. So starting from the top, if we have the limit as n approaches infinity of n squared times e to the minus n, what we need to begin with is thinking about this intuitively. For a large input, what does n squared e to the minus n approach? And I'm going to go ahead and begin by just rewriting this slightly. Note e to the minus n is equivalent to 1 over e to the n. So we now think individually, the top is going to be getting arbitrarily large. The bottom is going to be getting arbitrarily large. So what property do we want to apply? L'Hopital's rule. But I need to make a very important observation. So we cannot apply L'Hopital's rule directly to a sequence. And this is a very key but subtle observation to make. L'Hopital's rule cannot be applied, the key word here, directly to a sequence. But recall from our previous discussion, we have a property that tells us for this associated function, in this case for f of x equals x squared over e to the x, f of n is equal to n squared over e to the n, which is our sequence. So this limit of the sequence is also equal to the limit of this associated function. And we most definitely can apply L'Hopital's rule to functions. Now, if you're wondering why we cannot apply L'Hopital's rule to sequences, remember a sequence is a list of numbers. And to use L'Hopital's rule, we have hypothesis related to continuity, and we have to be able to differentiate. And there's no concept that we have of differentiating a list of numbers, but instead we differentiate a continuous function. So it's a subtle point, but it's really something that gets to the heart of mathematics in making sure that hypotheses are satisfied. So now this is a familiar problem. The top goes to infinity, the bottom goes to infinity. That means we can apply L'Hopital's rule. So we have the limit where we differentiate the top and we differentiate the bottom. The top still goes to infinity, the bottom still goes to infinity. So we apply L'Hopital's rule again. We take the derivative in the top and the derivative in the bottom. Now the top is approaching the constant 2 while the bottom grows indefinitely. So what is the value of this limit? 0. Now note, if you apply L'Hopital's rule directly to the sequence, you would still get back 0. But remember, the correct answer found by incorrect means is not correct work. So one last time I'll reiterate, we cannot use L'Hopital's rule directly with a sequence. With that in mind, we have 2 examples remaining, and it is a perfect time for you all to pause the video, give yourself maybe 5 to 7 minutes, and go ahead and evaluate the 2 remaining limits. So for this first limit, the observation I want to make is it's a degree 2 over a degree 2. This is something we spend significant time discussing when we are in Calculus 1. You most definitely can apply L'Hopital's rule to it, but I think it's simpler, at least in terms of the math we use, to use our previous intuition. Multiply by 1 in the fancy way. 1 over n squared divided by 1 over n squared, where that 1 over n squared is coming from looking at the largest power of n in the denominator, just like we discussed in our first video on sequences. So distributing that 1 over n squared through the top and the bottom, we would have 3 over n squared plus 5 divided by 1 over n plus 1. And then we can go ahead and we might say limit law this thing to death, right? You take the limit of the top over the limit of the bottom, and in the top and the bottom you can break it up into two separate limits. So that would be the limit as n approaches infinity of 3 over n squared plus the limit as n approaches infinity of 5 divided by the limit as n approaches infinity of 1 over n plus the limit as n approaches infinity of 1. And then finally, all of these limits are extremely reasonable. As n approaches infinity, 3 over n squared and 1 over n will both individually go to 0. And the limit of a constant is always that constant. So 0 plus 5 over 0 plus 1 gives us back 5. Now in the remaining example, with the limit of the ln of n squared over n, this is definitely a scenario where L'Hopital's rule is going to be necessary. The natural log is going to infinity, and n is going to infinity. But remember, not to sound like a broken record, we cannot apply L'Hopital's rule directly. So we write this in terms of x's. And note, for any given sequence, if you replace each and every n with an x and take the limit as x goes to infinity, whatever that limit converges to, so will the limit of a sequence. That was one of our key properties from the previous video. And I am perfectly fine with you just making that jump. If you want to note something like this to the side, you certainly can, but it's not required. So the top is going to infinity, the bottom is going to infinity. So we apply L'Hopital's rule. L'Hopital's rule allows us to evaluate the limit where we've differentiated the top and we've differentiated the bottom. In the top, we're going to use the chain rule. So the derivative of the outside evaluated at the inside times the derivative of the inside. And this would be the limit as x approaches infinity of 2 ln of x over x. And we're getting there, right? Note as x goes to infinity, ln of x goes to infinity, and so does x. So we need at least one more, and most likely our final application of L'Hopital's rule. Take the derivative in the top, divide by the derivative in the bottom. And simplifying as a single fraction, this would be 2 over x. And exactly as we noted previously, as x goes to infinity, the bottom grows indefinitely large, whereas the top is always this constant value of 2. So the number 2 divided by something arbitrarily large is approaching 0. Something else that's worth kind of reiterating is that our work when evaluating these limits should essentially look like what we see on the screen. We should be using good mathematical notation, writing a limit at each step until we're done evaluating it, fully justifying when we use L'Hopital's rule. And whenever possible, we want to organize our work in a single vertical column. But of course, as you're working down in a column, if you run out of space, draw an arrow up and start a new column. And at this point, we've finished the portion of our discussion related to using limit laws and properties to evaluate limits, and you're at a perfect position to begin working or continue working suggested problems from the book. And as you have questions, do not hesitate to reach out. So stay tuned. Take care.